Hi there, thanks for joining us. My name is Andrew Dunkley, and this is Space Nuts, a Q&A edition. It also happens to be our 600th episode, believe it or not. And what are we doing special today? Nothing. We're just going to answer audience... Well, it happens so often now. We're just going to answer audience questions, and we've got a bunch of them. The question of dark matter and dark energy theory has come up again. In fact, one of our listeners has come up with a theory about dark matter and dark energy theory, so we'll investigate that. We also have a question from somebody using a very interesting pseudonym, finding where our sun was born. I think we've been down that road before recently, so they're revisiting that. The temperature of black holes has been raised yet again. We talked about that recently. And Peter has asked us about the expansion of the universe. That's all coming up on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Once again, joining us from the... it's not the 600th time because we've had time off, so it's probably 592 or something like that. Maybe, I don't know, maybe a few less. But his name is Fred Watson, Professor Fred Watson, in fact, astronomer at large. Hello, Fred.
How are you doing, Andrew?
I'm
good
good.
to see you again.
Good to see you too.
Yep.
Can you believe it's 600 episodes? My goodness.
So because we now have 2 a week, that means we go through 100 every year, basically, doesn't it?
More or less. Yeah.
Whereas it used to be every couple of years. So
yes, we're just moving faster. It's the expansion of the universe because it's accelerating. That's what it is.
It's a relativistic effect. Right?
Indeed. Let us get straight into our questions because we've got a whole bunch of them. Daryl has sent us in a question. G'day, Space Nuts. I've been giving dark energy and dark matter some thought. If I've got this right, dark matter pushes the universe apart or away, while dark energy attracts or brings stuff together. So could dark matter and dark energy be the same thing but have like a north and south pole, i.e. dark matter north would be the particle that clumps together and dark energy south would be the particle that pushes outwards, creating negative pressure and expanding the universe? Thoughts? Now, that's his question, but he says, by the way, Martin's joke about the Gnab Gib being a lost BG brother made me laugh out loud for a couple of minutes. That's Daryl from South Australia. Yeah, I thought it was funny too. And that's the first time Martin's ever been funny. But no, it was a good one. It was a very good one. Yes, so this is an interesting theory. There's a dark matter south pole, dark energy north pole, opposites attract type of scenario. I don't know. What do you think?
So the issue, yes, it's a nice thought, because we naturally think along those lines when we recognise that one of these forces, entities, pulls stuff together and the other pushes it apart. And in many ways, that's the crux of the matter, because the two of them are fundamentally different in their effect on the universe. So dark energy, which comes as which is manifested to us in the accelerated expansion of the universe, that's an energy of space itself. And to the best of our ability to determine these things, it is isotropic. In other words, it's the same in all directions. Now, some people have questioned that, suggesting that maybe, for all we are looking at a big chunk of the universe with a horizon of 13.8 billion light years, it may be that that's just a small part of the universe, and there are other bits where the acceleration is not. Sorry, the expansion is not accelerating, and the two sort of even out. That's a caveat that we can't really deal with, because we've no idea what happens beyond the little bubble of the universe that we can observe.
Yeah.
And certainly it's true. Within that bubble, the acceleration is basically the accelerated expansion is basically the same in all directions. So it's a property of space itself. It's a fundamental property. Whereas dark matter, yes, that's got gravitation and pulls stuff in. It's definitely clumpy. It actually, it follows the visible matter. That was the way it was thought to be when we first started thinking about dark matter. But now we think it's probably the other way around, that the visible matter is visible because dark matter acted as a kind of scaffolding in the early universe for the gravitational pull of dark matter in order to bring the clouds of hydrogen together, compress them and make them turn into stars. So that's why dark matter and normal matter stick together. But they do stick together. And when you observe the universe on the larger scales, we can see by, for example, gravitational lensing, we can see that the dark matter definitely follows the visible matter. So there will be places where there's hardly any visible matter and there's hardly any dark matter, whereas with the dark energy, it's everywhere. Yeah. And so there are fundamental differences between them. And I suspect in the end, if we were having this conversation in 20 or 30 years' time, we probably will be, actually. But anyway, when we look back on this, we might have realized that the dark energy is a boson. It's a force particle, whereas dark matter is some sort of matter particle made of quarks and things of that sort. So there are probably fundamental differences rather than just that sort of the idea that they might be the same thing but with a different polarity. Yeah. I don't think the evidence supports that.
I suppose we could say Daryl's fallen for the naming error of these two things because we've said all along that dark energy is poorly named. It's not really the right thing to call it.
Well, neither of them are really. They're invisible would have been far better. But dark, it was actually Fritz Vicky back in 1933 who labelled this stuff dark matter. He didn't know what it was, and he said there must be something there, which he was calling dark matter, that's providing enough of a gravitational attraction to stop clusters of galaxies from dispersing altogether.
Yeah. Interesting. They'll figure it out one day, but for now it remains a mystery. But there's got to be something in that connection between real matter and dark matter clumping. Like if you go somewhere there isn't much matter, there isn't much dark matter. So there's got to be some connection there that
there is. That's right.
That will give us the answer one day if we can figure out what the connection is.
Yeah, well, the connection's gravity, and it's the only.
We haven't figured that out either.
No, that's right. We basically we know how it behaves. We know very accurately how it behaves, but we don't know what it is. Yeah. Yeah.
It is indeed a mystery, Daryl. But coming up with an idea always is a good way to get people thinking, and maybe somewhere in the dark reaches of the internet, someone will hear this and go, "Hang on, Daryl's onto something." And then he'll go to his Wikipedia or his Encyclopedia Britannica or his Funkin' Wagnall, flick a few pages and go, "Oh, I've got it figured out, thanks to Daryl's question on Space Nuts." So, there are no dumb questions in astronomy, are there, Fred?
No, that's absolutely right. There's just dumb answers from the likes of me.
Thanks, Daryl. Great to hear from you. Our next question comes from the fjords of Norway. This questioner goes by the name of, some will recognise this, Slaty Bartfast. Listening from the fjords of Norway last week, someone asked the question about viewing the birth of the sun, and Fred answered with the hypothetical mirror in space. My question is, if we calculated the exact location in space for the sun 4.6 billion years ago and pointed a telescope at those coordinates, would we see anything?
Because Slaty Bartfast won an award, didn't he, for the fjords of Norway? So
that's right. That's right. Yes, that was it. Because he designed them or
designed them. Yes,
yes.
He made fjords.
That's right. That was what Slaty Bartfast was famous for.
One of my favourite Douglas Adams characters.
Oh, yeah. I think the moment where he's forced to say his name is one of the funniest moments I've ever experienced. Because first time I ever listened to it, I listened to the audio version, that just caught me so beautifully. I just couldn't stop cackling.
No, it's epic stuff. One of the all-time greats in science fiction.
Absolutely, yes.
Yeah. Anyway, the answer to Slaty Bartfast's question is no. So do you want to keep going?
Well, I mean, he's basically saying, so you're saying we would not see anything if we could figure out where the sun was 4.6 billion years ago and then pointed a telescope at it?
Yeah, because first of all, the sun isn't there anymore.
No, I know where it is.
Yes, the odds are
it's over there.
That point, let me see, which way you're pointing?
I'm pointing that way.
That way, that's good. That's probably correct too. In fact, it's behind me too.
Yes, it's to my right rear.
Oh, right, okay.
At the moment.
That's a bit intimate, isn't it? Anyway, never mind. The
sun is certainly not shining out of that particular part of me at the moment, but it's in that kind of direction.
It's what all your fans think, though, isn't it?
No, they don't. I don't even have any. I don't get fan mail. I get abuse.
Well, anyway, notwithstanding all that, what was the question again? Yes, if you could work out where the sun was 4.6 billion years ago and point a telescope at it, you wouldn't see anything because the point where the sun was formed, and it will be only a few, at most, 100 million light years away. So, yeah, you've got to look back time, but you've got to look back time, it's probably less than 100 million years. And the sun 100 million years ago was a lot like what it is now. It's slightly hotter and a few other things that were going on at the time, but not much different. But the fact is it's not there, it's here. So even, as I think I said in that thought experiment, you'd have to have a mirror, something like 2.3 billion light years away, which is going to take you quite a lot of time to put in place anyway. But if that mirror was looking back to wherever the sun was formed, and we don't know where that was, we know it's within the present vicinity of the sun because stars don't move that fast. Anyway, you have this mirror and you capture a reflection of the sun being born. That thought experiment, I think, would work. But just looking at where the sun was when it was born isn't going to tell you very much.
There's got to be something there, though, Fred.
Well, there'd be, probably other stars and things like that. It's just part of the solar neighbourhood.
Yeah. Our sun, I suspect, came from, a pretty rough neighbourhood, and that's why it left. It inherited money and managed to get away.
Yeah, but then it discovered drugs, didn't it? That's the trouble.
That's what happened.
What happens.
Yes, and then we turned up, and all hell broke loose. Yes, but no, there'd be nothing to see there. Nothing to see there. No,
nothing that's really of any interest. Just other stars.
Yeah. Although we're still looking for Earth's siblings. The sun's siblings.
That's right.
Because there would be some, but they wouldn't be there either, would they?
Well, the stars the stars that were born alongside the sun in the same cloud of gas and dust are probably not that far away, but they, 100 million light years I mentioned before. It's probably much, much less than that. I don't know quite why I thought of that, but anyway, because the centre of our galaxy is only 25,000 light years away. So I probably meant 100,000 light years when I said 100 million. Something's going wrong with this program today. I'm not quite sure. Well,
It's our 600th. It's our 600th.
that's what it is.
We're
That's
tired.
what it is. There's a gap in space time has opened up, which I'm floundering in at the moment. Yeah. So you might. It's not gone very far. That's what I'm saying. The siblings from the sun, born in the same gas cloud from the sun, are probably within. They might even be within the nearest 100 light years, not million light years.
Gotcha.
That's why we can use very high resolution instruments, ones that really analyze the spectrum of a star in great detail, but need the star to be relatively bright. That's why we can use that technology with the real hope of finding the solar siblings, because it's by analyzing the spectrum, the chemical composition of a star in very great detail. That's how we would identify that a star had exactly the same chemical composition as the sun and could be regarded as likely to be a solar sibling.
Okay. We may one day find one of them, but who knows? Yeah. We'll see. And thank you, Slaty Bartfast. Whatever your real name is, maybe that's it.
Could be.
Thanks for the question. And thank you for sending me the Babel fish so I could read the question. That was a good idea. Very, very good idea. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson. Let's take a break from the show to tell you about our sponsor, NordVPN. Now, if you've ever felt like your online privacy is slipping through the cracks, then you're not alone. Hackers, scammers, harvesters, they're all out there trying to get your private info, whether that's your passwords or your personal details to sell on the dark web or to use themselves to access your bank accounts, credit card details, and who knows what else. But you can protect yourself with NordVPN. You can take control at home or more importantly, when you're out in public using free Wi-Fi. Right now, using the exclusive Space Nuts offer, you can receive 4 extra months for free on a NordVPN.com plan. NordVPN encrypts your internet connection, hides your IP address, and offers access to over 7,700 servers around the world. Plus, with features like Threat Protection Pro, MeshNet, ultra-fast speeds via NordLinks, your digital life stays private and efficient. So don't miss out. Visit nordvpn.com/spacenuts and enter the code SpaceNuts to claim this deal. Remember, there's a 30-day money-back guarantee, so it's risk-free to try. Stay safe, stay private, and browse with confidence. That's nordvpn.com/spacenuts and use the code word SpaceNuts. nordvpn.com/spacenuts.
Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem. We've had a main beam bus undervolt.
Roger, main B undervolt. Okay, stand by, 13. We're looking at it.
Space Nuts.
You know, that moment where they realised they had a problem on Apollo 13 sounded much better in the movie. It just, yeah.
No, you broke up exactly
did.
as you were saying.
I noticed that, and I
So
was going to keep talking until you came back, but
Tell me what you said.
I said that moment where Apollo 13 realised they had that problem sounded much better in the movie.
Well, yeah.
Wasn't nearly as dramatic in real life, was it?
Well,
It was dramatic, but the way they announced
absolutely.
it, they basically just said, yeah, this button didn't work. More or less.
Yeah, epic stuff. I mean, it still gives me tingles, does Apollo 13.
Absolutely, yeah. Now, Fred, let's move on to our third question. This one comes from Bjorn.
Good evening, Fred and Andrew. I have to thank you for a fantastic podcast. My first choice every evening among lots of interesting stuff. It's the first one I choose. It's regarding the question you had about temperature of black holes. I must ask you to clarify if material accretes close to the event horizon, it's millions of degrees hot. If I follow the material spiraling inwards, it does not suddenly become cold when it enters the event horizon, right? It's still extremely hot, maybe even hotter, even if it's supposedly hard to measure because it's hard to get a thermometer in there and have a reference. But it's extremely hot. That seems cold to an outside observer because it does not radiate anything. But maybe it could be clarified somehow. It's not magic that it suddenly gets cold. It just stops emitting, right? Take care. It's Bjorn from Gothenburg. I love your show.
Thank you, Bjorn. That Babelfish is working well because his English was excellent.
He lives in a nice place as well. Gothenburg's got a very nice city centre with a lovely opera house.
Yeah, I haven't been there. In fact, I haven't been to Sweden yet, but it's on the wish list. So we'll see how we go.
It's great.
Now, he's referring to a question that came from Casey in Colorado when she was asking about the temperature of a black hole. So he's basically kind of saying, look, I understand what you were saying when you answered Casey, but now everyone thinks they're cold when they're probably not cold. They're just not emitting anything. Is that right?
Yeah, that's right. They're cold because they're not emitting anything. But Bjorn's right that, the temperature of the accretion disk and probably the way to look at it is the temperature of the event horizon is millions of degrees because that's where all this stuff is circulating at high speed and with huge amounts of energy and emitting X-rays. It disappears over the event horizon at very high temperature, and presumably within the event horizon, it's still got that high temperature. But then it hits the black hole, it's sucked in, and if you could measure the temperature of the black hole itself, you'd find it was virtually absolute zero, very, very small temperature.
Okay.
Because it's not emitting anything, stuff's going in. And it is hard to imagine, and Bjorn mentioned magic, and that's almost what it is, stuff that's going in at very high temperature. But if you could measure the black hole itself, supposing it stopped accreting material, and you could then measure its temperature, it would be virtually zero.
Well. They are so complicated, though, aren't they? I mean, we're still learning a lot about black holes, and we're starting to image a few of them. We've got a couple of good pickies now, but they are still mesmerizing and mystifying because until dark matter came along, we got more questions about black holes than anything else. They are the thing that people want us to unravel in terms of understanding. But I think we're a long way away from that at the moment, aren't we?
I think, that we know a lot about black holes, considering that 60 years ago, nobody believed they existed.
Yeah, I'll leave the point.
And we've observed them. We've actually observed the radiation coming from the accretion disk, the region around the event horizon. We've observed effectively the shadow of the event horizon of several black holes now, and even detected the polarization of the material that's being sucked into it. And this is extraordinary stuff. These are measurements that really only a few years ago would have been thought to be impossible, but we're, I think, doing it rather well. So we're still learning about black holes. They are, and that's the reason why they're so fascinating is that they are completely counterintuitive. How do you have something that's simultaneously at 0 and a million degrees? And that's what you've got. So it's they're still very, very interesting objects.
But back to Bjorn's question, the temperature is 0, absolute 0 or thereabouts because of the fact that it doesn't
radiate anything. Yeah,
exactly.
So the way to imagine it, I think, and this probably puts it more succinctly. Yes, while while it's accreting, you can't see the black hole because it's surrounded by this hot material at very high temperature that's being swallowed into it. But if that supply of gas ran out and the black hole stopped accreting, then you could measure its temperature, then it would be zero, effectively, be absolute zero. A little bit above, but not very much.
Okay. There you go, Bjorn. And I'm looking at photographs of Gothenburg. It is an absolute beauty of a city, isn't it? What a lovely part of the world. So, yeah, very lucky. Nice trams. Thanks, Bjorn. Great to hear from you in Sweden.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
And believe it or not, our next question comes from Sweden. Does the expansion of space mean that the universe gains more meters, or are the meters becoming longer? Related to this, is it space only that is expanding, or is it space-time? If so, what's happening to the time part of it? Is time expanding too? What would that mean? Thanks for a most interesting podcast. Peter from, I'm going to pronounce this incorrectly, Falun in Sweden. So, yeah, hopefully I got that right. My Babel fish can't translate back into Swedish.
Well, if you put it the other way around...
Got to put in the other ear.
Yeah, that's right. That'll do it. Yes, that's a great question. And so my view, the intuitive view, which is based on a few years of thinking about this kind of thing, the meters are becoming longer. And that's sort of illustrated by the fact that the wavelength of radiation is getting longer. That radiation had a particular wavelength when it was emitted. And as the universe has expanded, whatever it's coming from, whether it's a distant galaxy or a quasar or whatever, as the universe has expanded, that radiation has been stretched, which means that the meter's been stretched because the frequency remains the same. Except when you observe it from our vantage point in the depths of the universe. Yeah, forget about the frequency. That's a furphy. But the wavelength stretches. So the length scale is increasing. In fact, there's a thing called the scale factor of the universe, and it's very easy to prove. It's one of the most simple geometrical equations in cosmology. The scale factor of the universe, now compared with when the light was emitted, the ratio of the two is equal to 1/1 plus z, where z is the redshift of the light that you're measuring. And so there's this direct link between the sort of scale size of the universe, which is the length of a meter effectively, and the redshift that we measure when we look deep into the universe. You look as though you've got a question.
No, I'm confused. So what you're basically saying in regard to his question was that the meter is expanding. So a meter is not a meter.
Well, it's still a meter, but it's a different meter.
Okay.
Because the scale factor of the universe was less when the light was emitted. This is the thing, you've got two different reference frames here. That's why this stuff gets a little bit complicated, because in our reference frame, the meter is longer. But if you were traveling along with your meter stick, as it sped through the universe, it would be changing in length. It would appear to be the same length.
Right. I'm sorry. This is just... It's mind-bending, isn't it?
It bends mine as well. And so something similar happens to time. But once again, so we're still inside the universe, but we're observers in a different reference frame from when the light was emitted. Because that's what we're talking about. We're talking about being able to measure the expansion of the universe through the light waves. So, and we know that time dilation took place. We can measure that by looking at the rise and fall rates of supernovae in the distant universe, and they actually appear to rise and fall slower. So it is the time element of that changes as well.
Okay. I think he chose a meter because the meter was defined by the International System of Units as the length of the path light travels in a vacuum during a time interval of 1,299,792,450 eighths of the second.
Yeah, that's how it's defined today. It was originally defined as being, what was it, 1/400,000th of the circumference of the Earth? I can't remember.
Yeah, I can't.
Something like that.
Right. Okay, so
no, it would be 140. Anyway, so it was related to the circumference of the Earth.
Right.
I can't do the sums anymore. My brain's fried today. I don't know why. I mean, you're right. I think it's episode 600.
Yeah,
there's a relativistic phenomenon taking place here.
It's just messing us up. I mean, we need a holiday of some kind. But anyway, hopefully that helped, Peter. I don't know. But I think somewhere in there we did answer your question. Thanks for sending it in. And good to have a very Scandinavian sort of 600th episode. So, I mean, we've got Slaty Bartfast, we've got Sweden a couple of times over, and Norway, and then South Australia. Okay. Well, no, anyway, close enough. Close enough.
South Australia is not known for its fjords, but it is a nice place.
It is a lovely place, except it was pouring rain and gale force winds when we visited. But anyway, that's the way it goes. Thank you, Peter, Bjorn, Slaty Bartfast, and Daryl for sending in questions. If you've got questions for us, please send them in to us via our website, spacenutspodcast.com, spacenuts.io. Click on the AMA button, which stands for Ask Me Anything, and send us your text or audio questions. Don't forget to tell us who you are and where you're from. We'd love to hear from you, especially if you haven't sent in questions before. Also, if you'd like to help us out, please, wherever you listen to us, leave reviews, because the more reviews, the better. The more we move up the relativistic food chain that is podcast world, and we get more listeners, perhaps. That's the aim of the game. Anyway, if you could do that for us, that'd be great. And Fred, thank you very much. Nice to chat. We'll catch you on the next episode.
Sounds great, Andrew. Hope we get our breath back before then.
Yes. It's been a bit tiring, hasn't it? But we got there in the end. Professor Fred Watson, astronomer at large, and he'll be back with us next week. Hugh in the studio, we thank him too for all the work he's done over these last, well, actually, he doesn't turn up for most, so the last 4 episodes that he's been with us. In fact, he couldn't be with us today because we told him he could have every 600th episode off. And from me, Andrew Dunkley, thanks for your company. We'll see you on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.